Euler's formula gave us a remarkable fact. The complex exponential is a rotating arrow. Now we will use that single rotation to build, and then analyze almost any signal. Euler tells us that e to the I theta equals cosine theta plus I sine theta. The horizontal axis is real, the vertical axis is imaginary. The rotating point has coordinates cosine theta and sine theta. Its horizontal guide preserves the same height and traces sine theta across the horizontal graph. Its vertical guide preserves the same sideways displacement and traces cosine theta down the vertical graph. The two curves are perpendicular shadows of one rotating point. Replace theta by n theta. The arrow now completes n turns while theta completes one. Its shadow becomes sine of n theta. One turn is the fundamental frequency. 2, 3, and 4 turns are its harmonics. A rotating arrow needs more than a frequency. Its length sets the amplitude, and its starting angle sets the phase. Both are stored in one complex coefficient, c sub n equals a sub n times e to the I phi sub n. Now connect several rotating arrows head to tail. Each arrow turns at its own frequency, with its own amplitude and phase. Their final endpoint moves according to the sum of all those simple rotations. Project that endpoint onto one axis. 3 simple sine waves become one complicated waveform. This is Fourier's central idea. A complicated periodic signal can be understood as a sum of simple circular motions. But how do we discover the hidden rotations inside a signal? Suppose we want the component with frequency m. Multiply the whole signal by e to the minus im theta. Geometrically, we rotate our viewpoint backward at exactly frequency m. The component we want stops rotating, because e to the im theta times e to the minus im theta equals 1. Every component with another frequency keeps rotating at the difference n minus m. Now average over one complete turn. A rotating arrow visits every direction, so its vector average is 0. But the selected arrow remains fixed. Its average survives. This is how Fourier separates one frequency from all the others. The algebra says the same thing. For k not equal to 0, integrate e to the I k theta over a full turn. The endpoint returns to 1, so the numerator becomes 1 minus 1, 0. For k equal to 0, the integrand is 1, and the integral is 2 pi. Therefore, the full turn average of e to the I times n minus m theta is 0 unless n equals m. This is orthogonality, represented by the Kronecker delta. Multiply the Fourier sum by the backward rotation and integrate. Every unwanted term vanishes. Only c sub m remains. So c sub m is the average of f of theta times e to the minus im theta. The signal is built by summing the rotations. The coefficients are recovered by testing the signal against those same rotations. These two equations are the complex Fourier series, synthesis and analysis. A time domain measurement may be pressure, voltage, or displacement. Now let algebra and picture match exactly. On the left, S1 is 0.8 sine of omega 0t. S2 is 0.45 sine of 2 omega 0t plus 0.5, and S3 is 0.25 sine of 4 omega 0t minus 0.3. Each term draws one colored wave. Add their values at the same time, f equals S1 plus S2 plus S3, producing the middle trace. The spectrum on the right stores the same components as peaks. The coefficient sets peak height. The frequency sets horizontal position. The phase shifts the wave in time. One term, one wave, one peak. A periodic signal has separated, discrete frequencies, but a single pulse does not repeat. Let the period grow. The allowed frequencies move closer together. In the limit of an infinitely long period, they form a continuous frequency axis, and the sum becomes an integral. That limit is the Fourier transform. Multiplying by a backward rotation tests one frequency. Integration accumulates what stays aligned and cancels what does not. A short pulse, therefore, requires a continuous band of frequencies. Euler's identity is the engine inside Fourier analysis. Circles become waves, waves become spectra, and measurable complexity becomes a sum of simple rotations.